Our next talk is by Jamie Brandon, and he's going to be talking about Julia as a platform for language development.
All right. So I'm going to talk about using Julia to develop other languages, which is something I've been doing for a while now. I sort of fell into this accidentally about oh wow, the font size is different here. That's terrible. Well, it's going to look like that for the rest of the talk. So yeah, about 5 years ago, I was working at a startup called Eve that was building a programming language for sort of live coding credit apps. And we built everything in C and JavaScript and later on Rust. And it was terrible. It was incredibly hard. And we spent most of our time doing the sort of like grunt implementation work of making a language work and debugging it and making it fast, rather than the actual like novel, interesting things that we were trying to produce. So after I left Eve, I spent a bunch of time working on different experimental projects trying to figure out better ways of doing this. And I ended up building a lot of stuff in Julia. Most notably, this data block compiler I wrote entirely in Julia, like 500 lines of Julia, and it ended up being sort of 10 to 100 times faster than Postgres on some fairly large benchmarks, which is pretty fun. And then I spent the last year or so working at a company called Relational AI, there are a couple of people around here from the same company, building a very ambitious project that requires building a database engine and a query language, probabilistic programming languages, machine learning algorithms, and so on, to do in database machine learning and take your entire data pipeline and optimize it all in one place. And that sort of not coincidentally ended up being almost entirely written in Julia. And I think people were quite skeptical when we first proposed the idea, but by now everyone's pretty on board with this having been a good decision. So this is not what the rest of the PL community is doing. So when we talk to people in the larger community, we get advice like we should do the metaprogramming in a language like Scala and generate code, C, LLVM, Rust, whatever, for the performance-intensive systems code, and the code needs to order massive data. Scala or Haskell will do well, and doing it in Julia sounds more like a party trick to me. So this is basically what the rest of the PL world thinks about using Julia for this task. But they also say to do all our compiler work in one language and generate code in another language, which sounds awfully like having a two-language problem, which is exactly what Julia was designed to fix. And so the question is why do people not take this seriously? And I think the answer is that Julia has a marketing problem, because if you look at Julia from a distance, you hear that it's a dynamic language and it has a JIT, and you basically just file it under, JavaScript with matrices, some opaque black box that will take your incredibly dynamic, crazy code and make it fast sometimes. And when it doesn't, then there's nothing you can do about it. So this is what I would like to tell people who live in this world. So if we're talking about Julia as a language for writing compilers, we have this sort of Lispy heritage of code of data and quasi-coding and eval, which makes it very easy to produce code and run it. And we also have algebraic data types, sort of pattern matching, and the ability to use metaprogramming to really easy produce generic traversals over abstract syntax trees, which is what mostly compilers do. And strong parametric dependent-ish types, people get angry about that. And interactive development, which is a big deal not just for the increased development speed for us, but because in the early days of prototyping a language, you have to make the tools to interact with the language. And it's really nice to be able to just put the language in a string macro and then just dump it in Juno or Jupyter or whatever, and not have to build any of our own tools. And then as a compiler target, the number one thing for me is predictable performance. Compared even to writing code for, say, the JVM, Julia gives you so many tools for understanding what's going to happen to your code and finding out what went wrong when it doesn't run fast, that you can actually build an intuition and a mental model that helps you design code in advance rather than have this sort of long feedback cycle of trying things and finding out that they don't optimize nicely in the tracing JIT. And also sort of partial control over layout and the ability to stack allocate stuff. Not to the same extent that we could if we were generating LLVM, but certainly much more than if we were compiling languages to the JVM, which doesn't have user-defined value types even. And hooks into the compilation process. GoTo, which is in there. People keep it quiet, but it's available. which is really nice. A lot of the algorithms I had to compile are basically giant state machines, and GoTo makes that a lot easier. And also the sort of escape hatches via SQL and LVM call, and having raw pointers with no performance overhead compared to C. So a lot of the relational I, we're dealing with data that is way bigger than available memory, and so we're building these complex on-disk data structures, and we need to be able to operate on those directly without paying for like deserializing the whole thing into memory and basically having 2 copies of all of our data. So what is everyone else doing instead of using Julia, which is the obvious solution? So the community at least sort of acknowledges that this is a problem. You look around, you can find a lot of people writing about this dilemma where as a language researcher, especially in academia, you'll come up with some cool idea like I propose that we have continuations or whatever in our language, and people say that'll never work, you can never implement that efficiently. And you say, yes, it can, and you come back 5 years later and say, okay, you're right. And the feedback loop is just way too long, especially for people who have to publish like 3 papers a year. And so people work on solutions to this. I think the sort of one that's been like successful in the mainstream is creating some virtual machine, and then everyone compiles our code to this virtual machine. So if you compile to Java bytecode or whatever, you get to reuse all of the JVM's libraries and garbage collection and tooling and the JIT compiler. And that all works really nicely as long as your language kind of looks like Java. So that's not a knock. I mean, we're going to talk about compiling stuff into Julia, and I think it's pretty much the same situation with Julia. Things that kind of are Julia-like, and that they sort of get type information and then do a bunch of computation after the type information is available, work pretty well in Julia. If you're trying to compile something like JavaScript into Julia, you're going to have a terrible time. So another approach that's more popular in sort of academia, but I don't know if any like big sort of actual like industrial successes with this is multi-stage programming. So you start by writing some very naive interpreter for your language, and you gradually transform it in a way that the structure stays the same, but you're adding chirps to the compiler at various points as type information becomes available. And finally, there's totally crazy approaches where you write an interpreter for your language and maybe add some annotations and feed it into some magic tool that turns your interpreter into a compiler. And so this was the idea behind RPython, which is what powers PyPy, and more recently there's a big group at Oracle working on this tool called Truffle. Both of these are tracing JIT compilers. So Truffle especially is written in Java, so you have a tracing JIT compiler compiling your tracing JIT compiler, which compiles your compiler. And I haven't like used Truffle a lot, but I don't know if you ever get to the point where that like makes sense and you understand exactly what's happening to your code. But I've seen people talk about like 5 minutes. They produce these amazing benchmarks, and there's a little asterisk saying like after 5 minutes of warming up all the various layers of JIT compilers. So I'm kind of dubious about some of these tools. But we can do all of this in Julia, pretty much trivially. I wanted to show like actual examples from some of our code, but there's just like so much context associated with them and so much code that it doesn't fit on a slide. So I'm going to really heavily simplify things and look at some very simple SQL queries. So say we want to evaluate this query. We have a train mini, which is some table of training data, and we want to count like how many rows in the training data fall on a date, which was a holiday, which was transferred from some other date. And so if we put this into Postgres, it comes up with a fairly sensible query plan, and it takes 137 milliseconds to execute this. And the question is how hard is it to do better than Postgres? Postgres internally is generating some query plan, which is a bit of operators, and that looks something like this. So we have a constant operator, which just feeds a relation into the query. Join operator, which it takes its input relation and joins it against some index. And a filter operator that filters out all the rows that don't match this condition, and a count, which counts the number of rows in its input. And so our SQL query might look something like this. We have a train mini being fed in as a constant, and the second column of train mini is being joined against this holiday events index. And then we filter out filter for all the rows where the last column is true, and then count them. And what's happening in Postgres is just a slightly more complicated version of this. And it runs it in an interpreter. And a sort of a naive version of this interpreter might have each of these operations take tables and return a table, but that ends up being terribly wasteful. You know, the output of this join would create a table, and you would then immediately iterate over the table, filter things, throw it away, make it a new table. So in practice, all of these operators will take an iterator and return an iterator. So this whole thing is nicely pipelined. So our iterator for a join operator might look something like this. Pretty straightforward code. We grab a row from the input iterator. If there are no more rows, then there's no more rows for the join. And if there is another row, we look it up in the join index. And if that returns a row, then we concatenate them together, spit that out. Otherwise, we go back to the beginning and try the next row. So in Julia, this kind of stuff is really nice and easy to write, and it performs absolutely horribly. This takes about a second to run, the same query that took Postgres 130 milliseconds. And it allocates 450 megabytes of memory, which is impressive because the input data is about 10 megabytes. So what went wrong here? The problem is that at compile time, Julia basically knows nothing about these join operators. It doesn't know what the type of the input to this join operator is, which means it doesn't know what method to call for iterate. And similarly now, we don't know what the return type of iterate is. So we don't know how to take apart this tuple. We don't know what the join key is, so we don't know which element of the input row we're getting, so we don't know what the type of this value is that we're looking at. We don't know what the type of the index is, and finally, we don't know what the type of either of these rows are where we can concatenate them. So every place where we have this missing information, we have to insert some dynamic dispatch. And also because we don't know the size of anything, all of the intermediate values have to be allocated on the heap, which is where that 455 megabytes of allocation comes from. So if we were database writers, our immediate response would be to write a compiler to fix all of this. So here's our compiler. The body of this code is basically the same thing we had before, but now instead of actually executing this code, we return it as a Julia expression. And everywhere that we had this missing information, we're splicing the actual values directly into the code. So that when Julia actually gets around to compiling this emitted code, it'll have all the information it needs to run this efficiently. And then we just eval this code. It becomes a normal Julia function, and we can work with it like any other Julia function. So we had this sort of property that we can sort of take parts of our problem and compile it and get back a function, and it doesn't become contagious and infect everything. You don't have to completely produce a compiler for your entire language just because you wanted to compile some subpart of it. And this is much faster, so 60 odd times faster, 9 times faster than Postgres even. There's an asterisk because this is a silly comparison. Postgres is not optimized for this kind of workload. But it gives you sort of a sense of scale, like how much you can gain by writing like a simple compiler for relational queries, and why everyone in the database world is so interested in this. And also, this manages to allocate, I say no allocation, that there's one mystery allocation that I haven't tracked down here. On all of the examples, I had this one 32-byte allocation. I think it's just for luck. Okay, so I glossed over some stuff. There's a bunch of confusing things in this compiler. For one thing, I'm returning a closure inside the coded code, which is weird. Like, why can we not just return the code that does the thing we want? And the answer is because some of the other query operators have to call this input iterator in more than one place. And if we just naively splice the code in, we get this exponential increase in the amount of code we generate, and eventually our compiler falls over. I've actually managed to make Julia out of memory when trying to compile queries. So we splice the code for the closure in at the top, and then we call the closure in these different places, and that prevents this problem. There's also this very sneaky let in here. Maybe you're thinking, why can't we just say input iterator equals? And the answer is because on the right-hand side, where we're splicing in the code for the input iterator, that might also say assign some variable like input iterator. So when we're writing a compiler, we suddenly have to make our own lexical scoping. And people invented lexical scoping for a reason. So the Datalog compiler I mentioned earlier compiles all of the code. And I spent 3 months working on it, of which about 2.5 months were just tracking down stupid bugs like this. So it'd be nice to get lexical scoping back. And in this case, because all we're doing is trying to convey information to specialize on, we don't actually need to emit code, we can just emit a closure. So we return a function, and we extract all the information that we want this function to specialize on. And because we want to specialize on the value of key and not just its type, we have to lift it into a type on the outside and remember to unlift it back inside. Where this lift and unlift are just using val to turn this value into a type. So again, this performs almost as fast as the compiler, and we now don't have to worry about silly things like lexical scoping and code generation explosion. But we still have this sort of two-step process, which is a bit of mental overhead to think about. So it'd be nice if we could just go back and actually write something more like the original naive interpreter. And if you think about why these closures work, what exactly is in a closure, we could just ask at the REPL with some formatting and renaming of things a bit. We can see this closure is just a struct that is parameterized by the types of the variables it closes over. And in fact, the field names are even just the names of the variables. So you can just grab the stuff out of it and poke around inside it. And it defines some method to call it. So we didn't even need this two-step process to begin with. All we need to do really is have these query operators parameterized by the types of the other operators that they're containing, which is probably what everyone in the room would have done to start off with, but then we wouldn't have this nice story of matching things to other approaches. And then all we have to do is when we assemble the query is to remember to lift this one value that we want to specialize on, and we get a simple naive interpreter code back, and just have to remember to unlift this value again. And this has the same performance as the compiled version. So a lot of commercial databases operators publish papers on how they go about writing the compilers, and generally the answer is they get a massive team together who write this big complicated compiler that spits out a whole bunch of C++, which they link back into the database. And you write a lot about like how all the problems that they have with this and how they mitigate all these problems, where really we just want to write this, right? Life is a lot easier in Julia. So I'll skip past this really quickly so we're running out of time, but we also like the sort of high-level parts of writing a compiler and doing these sort of rewrites. It's really easy to use it, let's say, a generator function to produce some like utility functions for traversing over these ASDs, which is nice when you have 30 or so operators in your tree. We wrote a pattern matching library so that we can easily write these operations. We have I think a couple of thousand lines of code now of just various transformations of different stages of the language. And having done this in a lot of different languages, Julia is so far the nicest, which if you had told me that 5 years ago I'd be writing all this stuff in a dynamic Lispy language instead of, say, Haskell, I would have been very surprised. Okay, so not everything is rosy. I run into a lot of problems, or I say a lot of problems, I run into the same problem all the time. So let's look at another example query. This takes some big table, applies a bunch of filters to it, and counts the results. This is all nicely pipelined, so it should be very efficient. Indeed, if our table consists of a huge list of integers, this is all fine. It takes about 4 seconds to run. There's 0 allocations. And none of these filters actually touch the second column of the table. And the second column is not actually used anywhere in this query. And so you would think that if we just change the second column to something else, it wouldn't matter too much. But if we replace the second column with some strings, it's about 3.5 times slower, and it allocates almost 60 gigabytes of memory. And the reason for this is really simple. We're representing rows inside this interpreter as tuples. A tuple of integers can be stack allocated. A tuple that contains a reference to the heap can't currently be stack allocated. It has to be heap allocated. And so every single time we produce a row anywhere in this interpreter, it goes on the heap in a new location. And when I talk to people about this problem, the difficulty we have in working around it, I usually told that don't worry about it because heap allocation is cheap. But the problem isn't the cost of heap allocation, but the problem of touching memory. So we can do some back of the envelope calculations. On my laptop, a cache line is 64 bytes. So scanning our big table is a billion rows, 2 columns, 8 bytes per cell. It's about 250 billion cache lines. If we additionally allocate a tuple for each one of those, for each row of that scan, we get about 1/3 of a billion extra cache lines. Best case, assuming these are all allocated contiguously and in order, and we can scan them nicely. More realistically, probably memory is fragmented, or these get they have to be aligned nicely, or things get moved around. And so the worst case, we have like a billion extra cache lines to read. The reality is probably somewhere in between these two, judging by our 3.5 times slowdown. And it's not just the extra memory. Like modern processors have a hardware prefetching, so if you access memory in a predictable pattern, they will start to speculatively fetch memory into cache before you ask for it. If you jump around your heap allocating all these tuples, you will break their predictions, and now you don't get the benefit of this prefetching. And even worse, when we're dealing with these huge out-of-code data structures, any heap memory you want to allocate means paging out some of the data we actually care about, and then we later have to page that back in, so the disk access is terribly expensive. So like ideally, like we need to keep all of our query code completely allocation-free where possible. And this is really hard because it turns up all over the place. So there's sort of like any tuples or rows that contain references to the heap. Anytime we want to return multiple things from a function, subarrays, substrings, which come from passing a bunch of hashing. The default hash implementation causes heap allocations. I know somewhere in the SQL, and regular expression matching, even if you just ask if something is a match, it'll handily allocate a substring and then throw it away behind the scenes. So avoiding this stuff becomes like the main subject of my working life. So there's a bunch of strategies we use to mitigate this. The Julia 0.7 has escape analysis, which only works within a single function, but if you inline aggressively enough, everything is one function. So the reason that there was a big stack of filters on the examples, it was if I only have one filter, then the whole thing gets inlined and the escape analysis kicks in, there's no allocations. Which is actually kind of a pain because it means we can't just test simple examples. Like we have to make stuff sufficiently complicated that we break inlining and see what the actual allocation patterns are. We can also just avoid actually referring to things directly. So rather than having row objects, we could just give the row number of the thing that we're talking about, and then all the later code has to know that we're talking about a specific table and has to know how to recreate that data when it wants to access it. So it's kind of like breaks composition, which is quite frustrating. And more commonly, we can, if we know the types of everything in advance, like if we don't have any like Julia or native functions inside our query, we can just pre-allocate mutable storage and reuse it. But it's itself like a subject of a lot of bugs. Like suddenly, you have, if you want to say quicksort an array, you have to remember to allocate 2 mutable tuples in advance because otherwise you compare 2 things and they're always equal. And I have some ideas. I haven't really fleshed them out about trying to reuse heap allocations because the problem is not that we're putting things on the heap, it's that we're putting them in lots of different places on the heap. If we could reduce the amount of locations that we used, it would mitigate a lot of these problems. So how am I doing for time? Okay. So this might get fixed eventually. I keep checking into these conversations. The last I heard, this is bottlenecked on upgrading to Julia 1.0 and then upgrading LLVM, and then these things can be optimized. But there is, hope somewhere in the future. I couldn't resist putting, most of the stuff I'm doing at Relational AI is like not really ready to be demoed yet, but I couldn't resist putting some kind of benchmarks in, and the benchmarks are in quotation marks because these want to be benchmarks when they grow up. But right now they're not very careful or precise. But I've been working with this Favorita data set from Kaggle. It's 6 tables, around 14 gigabytes of CSV, on a machine with 32 gigabytes of RAM. We want to join all the tables together to produce a feature matrix so we can do some kind of machine learning, whatever on it. And we definitely have enough memory to do this. It should be possible. I tried this in data frames. The first join takes 23 seconds, which is not bad. The second join runs out of memory because it's now allocated 3 copies of the entire data, which is far too much. JuliaDB, the first join takes 92 seconds, which is surprising. I would have expected to be sort of on par with data frames, so I'm not sure what's going on there. The second join through undef ref error. There is some bug in the handling of left joins. So I tracked it down and commented on this issue. And I tried query.jl just for completeness, but it took 190 seconds for the first join and allocated 60 gigabytes of memory. I think because it's internally just using like this like tuple row representation, so the stuff's just getting allocated all over the place. And then the second join also failed because it can't do left joins on things which aren't already data arrays. This is in the interpreter I've been working on. You can see there's very user-friendly front end to it already. So this spends 25 seconds building indexes and then compute join all 6 tables in 45 seconds. Or if you don't want to actually materialize an output, if you just want to iterate over it and feed to say like online stats or something, it takes less than 3 seconds and does basically no allocation. So that's a fairly big performance improvement. And so the sort of fundamental drive for a lot of the stuff at relational I is this sort of workflow where you take your database and join a whole bunch of stuff together to get a feature matrix, and throw this machine learning tool pays a huge cost at this point where you make a huge thing and then just iterate it over it. And so there's like even already like with this very simple implementation, you can see like the kinds of speedups you can get by optimizing across the both of these. Yeah, so maybe a party trick, I don't know. I would have liked to, maybe next year I would like to have some kind of more rigorous comparison against like actual like state-of-the-art databases. Right now we're still very early, but you know. I think we're already at the point where, personally, I am fairly convinced that this is the way forwards for building this kind of system. But I don't know how many other people I can convince just yet with these results. Okay, and that's it. All the code and the slides are up here for the examples. And, yeah.
Thank you, Jamie. Are there questions?
So having seen this kind of type level staging trick used in a few different places, one problem you tend to run into is that the more features you add, the more you end up with a whole programming language with an AST that happens to be stored as a type and then interpreted via like a stage generated function. So I was wondering if you'd run into issues with that and whether you consider alternatives like kind of maybe expressing this as imperative code and writing a compiler parser with that with cassette or something to optimize it as alternative ways of doing this.
I'm not really bothered by the fact that we're because the project to begin with is creating a programming language, and we're just abusing Julia specialization to do compiling for us. So the fact that we're secretly putting a programming language into our ASC is exactly the point of what we're doing. And on the operational side, the plan is to do some sort of Snowflake-like database. So the actual permanent data storage lives in one process, and the queries live in another process. So if we get to the point where we find like, oh, we generated like too much code, we just throw the process away and start a new one. It's not a big deal.
Okay, thanks.
Any other questions?
Yeah, cool.
No? Great. Thank you very much, Jamie.